This is the second module of chapter 6. In this module, we shall describe two methods to compute all eigenvalues and eigenvector of matrices. The first method is known as Rathis-Hausser method to find all eigenvalues of a square matrix, but this method is applicable if all the eigenvalues of the matrix are real. And the second method is known as power method, and the power method is applicable for any arbitrary matrix, but this method calculates only the largest eigenvalue, largest in the sense of magnitude, and the corresponding eigenvector. Now, we consider Rathis-Hausser method to compute all the eigenvalues of a matrix. The main principle of Rathis-Hausser method is stated below. Let A be an arbitrary square matrix of order n. In this method, a convergence sequence of upper triangular matrices A1, A2 ... is constructed, and it is assumed that this sequence of matrices be converged to the matrix A bar. Then the diagonal elements of the matrix A bar are the eigenvalues of the matrix A if the eigenvalues are real numbers. So, based on this concept, we describe the Rathis-Hausser method to generate the sequence A1, A2 up to An and so on. This method is basically depends on LU decomposition method, which is described in chapter 5. Initially, let A equal to A1, that means the first diagonal matrix is taken as the original matrix, and then A1 is taken as L1 into E1, where L1 and E1 are the lower and upper triangular matrices, with the diagonal elements of the lower triangular matrix L1 are taken as 1. That means Lii equal to 1 for all I equal to 1 to n, where n is the order of the matrix A. Then we construct the matrix A2, which is equal to E1 into L1. Note that A1 is equal to L1 lower triangular into upper triangular matrix, the product of lower triangular and upper triangular matrix, but the matrix A2 is the product of E1 into L1, that means the product of upper and lower triangular matrices. Note that the matrices A1 and A2 are similar because A2 equal to E1 L1, that one as by definition A2 equal to E1 and into L1, which is equal to E1 into A1 E1 inverse. That means L1 is nothing but A1 into E1 inverse, that one mentioned here, A1 equal to L1 E1 or L1 equal to A1 into E1 inverse. So, using this relation, it is easy to observe that the matrices A2 and A1 are similar matrices. So, the matrices A1 and A2 have same eigenvalues because they are similar. Now, the matrix A2 is factorized as A2 equal to L2 into U2 with Lii equal to 1. That means, the diagonal elements of the lower triangular matrix L2 are taken as 1. Then we construct the third matrix A3 equal to U2 into L2, where U2 is obtained in matrix A2, where the matrix A2 is factorized and L2 is the lower triangular matrix. This is another factor of the matrix A2. So, in this way we construct a sequence of similar matrices A1, A2, A3 and so on, and let this sequence of matrices be converges to an upper triangular matrix or a near upper triangular matrix A bar. If the eigenvalues are real, then all the eigenvalues are obtained from the diagonal of the matrix A bar. That means, the diagonal elements of the matrix A bar are the eigenvalues of the given matrix A. So, this is the main principle of the method, Rathis-Hausser method. Practically, this method is very complicated because it involves lot of computation. That means, we have to determine the L, that means the lower and upper triangular matrices by LU decomposition method, and then we have to determine next matrix by finding the product of two matrices. So, lot of computations are there. Sometimes the lower triangular matrix L is replaced by Q, where Q is an unitary or orthogonal matrix. The rate of convergence of this method is low. So, the shifting technique may be used to accelerate the speed of the convergence of the method. So, there is another modification is available of this method to accelerate the speed of convergence. Now, we consider a matrix of order 3 by 3. The first row is 1 1 1, second row is 2 1 2, third row is 1 3 2. Now, we determine all the eigenvalues of the matrix using Ratti-Hauser method. So, for this matrix A1 equal to A, which is equal to the product of lower and upper triangular matrices. Note that the diagonal elements of lower triangular matrix are taken as 1 1 1. Now, after computation of this equation, matrix equation, that means A equal to L1 into U1, we obtain 9 equations, and after solving this equation we get L21 equal to 2, L31 equal to 1 and L32 equal to minus 2 and so on. Now, we form the matrix A1 equal to L1 into U1, where the first matrix is the lower triangular matrix and second one is the upper triangular matrix. So, from this matrix we construct another matrix A2, which is equal to U1 into L1, and after multiplication of U1 and L1 we obtain the matrix this one. Now, let A2 equal to L2 into U2. The first one is lower triangular matrix and second one is upper triangular matrix. The elements of upper and lower triangular matrix are given by these equations. 9 elements are obtained by 9 equations, and hence A2 is equal to L2 into U2. So, first one is the lower triangular matrix and second one is the upper triangular matrix. Now, we form the third matrix A3 equal to U2 into L2, which is equal to, the first one is upper triangular matrix, the first row is 4 minus 1 1, second row is 0 minus 3 by 2 half, third row is 0 0 1 by 6, and the lower triangular matrix is 1 0 0 minus half 1 0, third row is 1 by 4 7 by 6 1. After multiplication it becomes a 3 by 3 matrix. Now, from this matrix we construct the matrix A3, which is equal to L3 into U3. The first one is lower triangular matrix and second one is upper triangular matrix. That means the matrix A3 is factorized as product of upper and lower triangular matrices, and these are the values of the elements of the upper and lower triangular matrices. And finally, A3 equal to L3 into U3, that means the product of lower and upper triangular matrices. That means the matrix A3 is factorized as the product of lower and upper triangular matrices. In this way we find the other matrices A4, A5, A6, A7. Note that the lower triangular part of the matrices A6, A7 goes to the zeros element. It is observed from the matrix A7, we noted that the first element of second row of the matrix A7 is 0.00158, it goes to 0, and the first and second element of third row of the matrix A7, these are 0.00008 and 0.00040. So, these are also goes to the element 0. So, we can conclude that the sequence AI converges slowly to an upper triangular matrix and the diagonal elements converge to the eigenvalue of the matrix A. Hence, the eigenvalues of the matrix A are approximately 4.79129 minus 0.99989, 0.20859. So, these are the diagonal elements of the matrix A7. So, these are the approximate value because the lower triangular part is not exactly 0 of the matrix A7. The Ratti-Hauser method is described to find all eigenvalues of any matrix. but this method is not applicable for all kind of matrices, but it is applicable if all the eigenvalues of a matrix are real. Also, the method is based on LU decomposition method, and we know that LU decomposition is not possible for any kind of matrices. The LU decomposition method is valid or applicable if all the principal minors of all order are non-zero. That means the Ratishausen method is applicable for such matrices if all the eigenvalues of the matrix are real and all the principal minors of the matrix are non-zero. Now, we consider another method called the power method to find the largest eigenvalue and the corresponding eigenvector. In power method, we assume that the order of the matrix A is n by n, that means A is also a square matrix of order n, and let lambda 1, lambda 2 up to lambda n be the n eigenvalues of the matrix M. And without loss of generality, it is assumed that the magnitude of lambda 1 is greater than the magnitude of lambda 2, greater than magnitude of lambda 3, greater than dot dot dot, greater than magnitude of lambda n. That means the lambda 1 is the largest magnitude eigenvalue and lambda n is the least magnitude eigenvalue of the matrix M. The eigenvalue lambda 1 is also called the first eigenvalue of the matrix M. That means the maximum magnitude eigenvalue is also known as the first eigenvalue of the matrix. Let capital X1, capital X2 up to capital Xn be the eigenvectors corresponding to the eigenvalues lambda 1, lambda 2 up to lambda n respectively. Then by definition of eigenvalues and eigenvectors of any matrix A, we have Ax1 equal to lambda 1 x1, Ax2 equal to lambda 2 x2, dot dot dot, Axn equal to lambda n xn. This is the definition of eigenvalues and eigenvector which is mentioned in module 1 of this chapter. Let x equal to c1 x1 plus c2 into x2 plus dot 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 cn xn, where x1, x2 up to xn are the n eigenvectors corresponding to the eigenvalues lambda 1 to lambda n. If the eigenvectors are distinct, then obviously the eigenvectors, these eigenvectors are independent, linearly independent, and they form a vector space whose basis, one of the bases is x1, x2 up to xn. Let capital X equal to c1 x1 plus c2 x2 plus dot 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 cn xn be a vector of such vector space. And now we multiply this equation, equation 2 by the matrix A, that means Ax equal to c1 Ax1 plus c2 into Ax2 plus dot 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 plus cn into Axn. And this equation becomes c1 lambda 1 x1, as by definition Ax1 equal to lambda 1 x1 plus c2 into lambda 2 x2, because Ax2 is nothing but lambda 2 x2 and dot 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 cn lambda n xn. Now I taken common lambda 1, therefore lambda 1 into c1 x1 plus c2 into lambda 2 by lambda 1 into x2 plus dot 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 plus cn into lambda n by lambda 1 into xn. So this is the equation number 4. Again we multiply the equation 2 by a square, a cube, dot 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 a to the power k successively and obtain the following equations. The equation 5 is obtained when the equation 2 is multiplied by a square. That means a square x equal to lambda 1 square c1 x plus c2 into lambda 2 by lambda 1 power 2 into x2 plus dot 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 cn into lambda n by lambda 1 power 2 into xn. Similarly, the equation 7 is obtained by multiplying equation 2 by a to the power k, that means a to the power k into x equal to lambda 1 to the power k into this expression, and a to the power k plus 1 into x equal to lambda 1 to the power k plus 1 into whole expression. This is equation number 8. Now, we know that the magnitude of lambda 1 is greater than magnitude of lambda I for all I equal to 2 to n. That means, we have assumed that the magnitude of the eigenvalue lambda 1 is maximum among the magnitude of the other eigenvalues. Then for large k, that means when k tends to infinity, then lambda I by lambda 1 tends to 0 for all I equal to 2 to n. That means the terms within the square bracket of equation 7 and 8 becomes a to the power k x equal to lambda 1 to the power k into c1 x1, and all other terms become 0. And from equation 8 we have a to the power k plus 1 into x equal to lambda 1 to the power k plus 1 into c1 x1, and all other terms of equation 8 are 0. Now, when k tends to infinity, we have a to the power k plus 1 into x equal to lambda 1 to the power k plus 1 into c1 x1. This is the second equation of equation number 9, and it can be written as lambda 1 into lambda 1 to the power k c1 x1, which is equal to lambda 1 into a to the power k into x. Note that the terms within bracket is nothing but a to the power k into x. So, equation 10 gives a relation between a to the power k plus 1 into x and lambda 1 a to the power k into x. So, lambda 1 is present in equation 10, and this is the largest eigenvalue of the matrix A. We know that two vectors are equal if and only if their corresponding components are equal. That means, a to the power k plus 1 into x suffix I represents the ith element of this vector. A to the power k plus 1 into x is nothing but a vector which is equal to lambda 1 into a to the power k into x I. Hence, from equation 10 we can write lambda 1 equal to k tends to infinity, that means k is large, a to the power k plus 1 into x suffix I divided by a to the power k into x suffix I, where suffix indicates the corresponding element or the ith element, and this is true for all I equal to 1 to n. So, equation 11 gives the largest eigenvalue of the matrix A, and that one is nothing but the lambda 1. Let x0 be an initial eigenvector. It may be any arbitrary vectors, it may be a unit vector or any other kind of vector. Generally, x0 is arbitrary, non-null and non-orthogonal to the eigenvector or vector x1. Let lambda power I plus 1 be the largest element in magnitude of z I plus 1, where z I plus 1 is an vector, is an intermediate vector which is equal to A into xi. A is the given matrix and xi is the vector. Therefore, xi plus 1, that means next approximate vector xi plus 1 equal to z I plus 1 divided by lambda power I plus 1. That means, the intermediate vector z I plus 1 is divided by the largest eigenvalue or largest element of the matrix or of the vector xi, and this is true for all I equal to 0, 1, 2 and so on. The number lambda power I plus 1 is the I plus 1th approximate value of the eigenvalue lambda 1. Then the largest eigenvalue is given by lambda 1 equal to limit k tends to infinity z k plus 1 suffix I, that means the ith element of the vector z k plus 1 divided by the ith element of the vector x k, and this is true for all I equal to 1 to n. That means, this is alternative expression to calculate the value of lambda 1. The vector x k plus 1 is the eigenvector corresponding to the eigenvalue lambda 1. So, this method gives eigenvalue lambda 1 as well as the corresponding eigenvector x k plus 1. Initial vector x0 is generally taken as x0 equal to 1 1 dot 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 1, that means all elements are taken as 1. But if this vector is not close to the eigenvector corresponding to the eigenvalue lambda 1, Then the iteration scheme 13, that means the scheme defined in earlier slide, does not necessarily converge to the eigenvalue lambda 1, that is the limit of the ratio z k plus 1 ith suffix by x k ith suffix, that means the ith element of z plus k divided by the ith element of x k may not exist. In this case, the initial vector must be changed. That means in this case we can take the initial vector x0 as the unit vector or any other vector. Sometime a unit vector may be taken as the initial eigenvector corresponding to the eigenvalue lambda 1. Now we consider an example to illustrate the power method to find the largest eigenvalue in magnitude as well as the corresponding eigenvector. Let the initial eigenvector be x0 equal to the column vector 1 1 1. Then at first iteration the intermediate vector z1 equal to a into x0. A is the given matrix and x0 is the column vector 1 1 1. After multiplication it becomes 6, 11 and 14. 14 is the largest element of this vector. So lambda 1 is taken as 14, that means the largest element of the vector z1 is taken as the first approximate eigenvalue lambda 1 and that one is 14 in this case, and x1 is obtained by dividing z1 by 14. After division the vector x1 is 0.42857, 0.785714 and the third element is 1. Next we apply the second iteration. In second iteration the intermediate vector z2 is equal to a into x1. After multiplication it becomes 4.214286, second element is 8.071428, third element is 8.714286. And note that the largest element of the vector z2 is 8.714286. So it is taken as the second approximate eigenvalue of the matrix A. That means lambda 2 is equal to 8.714286 and the matrix x2 is obtained by dividing z2 by the largest element 8.714286 and it is equal to this matrix, this column matrix. And we calculate third approximate or third intermediate vector z3 equal to ax2. After simplification it becomes this matrix or the column vector, and note that the largest element of this column vector is 9.942623. This element is the third iterated value or third iterated eigenvalue of the matrix A and which is equal to 9.942623, and the third eigenvector is x3 which is given by this column vector. The 8th intermediate vector is this one, corresponding vector eigenvector x8 is this one, and the 8th approximate eigenvalue is 9.664286. The 9th approximate intermediate vector is this one, 9th approximated eigenvector x9 is this one, and the corresponding eigenvector is 9.664465. Thus the required largest eigenvalue is 9.6645, correct up to 4 decimal places, and the corresponding eigenvector is the vector x9 which is equal to 0.4776, second element is 0.8869 and third element is 1. So this vector is also correct up to 4 decimal places. Also the power method can be applied to find the least eigenvalue of a matrix. For this purpose we assume that lambda 1 and lambda n be the largest and smallest in terms of magnitude eigenvalues of the matrix A. Let an intermediate matrix be equal to A minus lambda 1 I. Then the eigenvalues of the matrix B are lambda I prime equal to lambda I minus lambda 1 according to the shifting eigenvalues property. That theorem is mentioned in first module of this chapter for all I equal to 1 to n. Obviously, lambda prime n is the largest magnitude eigenvalue of the matrix B. So, by computing the largest eigenvalues of the matrices A and B, we can find the smallest eigenvalue of A using the formula lambda n equal to lambda n prime plus lambda 1. That means, by computing two largest eigenvalues of the matrices A and B, we can compute the minimum eigenvalue or least eigenvalue of the original matrix A. Again, if xn is an eigenvector of the matrix B corresponding to the eigenvector lambda n prime, then xn is the eigenvector of A corresponding to the smallest eigenvalues lambda n in terms of magnitude. So, the power method is used to find the least eigenvalue of the matrix A also. Now, we explain this method by considering an example. Let A be a matrix of order 3 by 3 and we have calculated the largest eigenvalue of the matrix A is 10.1962 and this value is obtained by power method. Now, we construct the matrix B defined as B equal to A minus lambda, lambda means the largest eigenvalue 10.1962 into I is the unit vector, unit matrix, and this matrix B is given by equation number 14. Now, since the matrix B is available, then using power method we can calculate the largest magnitude eigenvalue of the matrix B and it is obtained as minus 10.3924. Therefore, the smallest magnitude eigenvalue of the matrix A is lambda n equal to lambda n prime plus lambda 1, where lambda 1 is the largest magnitude eigenvalue of the matrix A and lambda n prime is the largest magnitude eigenvalue of the matrix B, and it is equal to minus 0.1962. So, minus 0.1962 is the smallest magnitude eigenvalue of the matrix A. In this module, two methods have been described to find eigenvalues and eigenvector of a matrix. The first method determines all eigenvalues of a matrix under certain restriction. The second method, that means the power method, can be applied to find the largest magnitude eigenvalues of any matrix and the corresponding eigenvalues and eigenvectors. And this method is also used to find the smallest magnitude eigenvalues and corresponding eigenvector. In next module, that means in module 3, we describe two methods to find all eigenvalues and eigenvector of a real symmetric matrix.